You're getting the points for it. All right, so I'm on page 209, 210. All right. Birds, cats, dogs. All right. So on page 209, this says a survey was conducted of an elementary children to see what kind of pet they would like to own, birds, cats, or dogs. Students are allowed to choose multiple answers. The Venn diagram records the results. Note the E equals 40 in the upper right corner indicate the total number of people participating was 40. Okay. So I got 10, 1, 2, 6, and 9. All right. That 40 that's up in the corner. So you have to be careful with this. Okay? And I will warn you if this does take place on a quiz. You have that 40. That means that we have 40 people total that are involved in this. So we have to figure out how many kids of that 40 do not want a cat, bird, or dog, or overlap of any of them. Okay? All right. So, I'm competing with voices, more than the ones in my head. I got 10 plus 10, 20, 21, 22, 23, 29, 38, 40. Okay, so we have nobody in there's nobody that is in our survey because I counted up all of our little segments. All the little segments added up to 40. So there's no kids at the school that don't have a cat, bird, or a dog or what they like. Okay? So as I go down, problem number 1, probability they like birds. Okay? So we have 40 kids total. Okay? How many of them like birds? So we're going to go to the bird one, the green one, and we're going to count up. I have 10 plus 1, 11, 12, 13, 14, 15. So I have 15 out of 40 kids that like birds. Now, of those 15 kids that like birds, some of them are overlapping with other groups, and that's okay. And then problem number 2, probability that not cats. They don't like cats. No cats. Okay? So what I'm going to do is I'm going to count up the kids that are here. So I got 1, 2, 3. So that makes 12. So I have 12 out of the 40 kids that don't like cats. Okay? Those are smart kids. They don't like cats either. All right. And then problem number 3 says probability that they like cats and dogs. Cats and dogs. That upside down U means and. Cats and dogs. Okay. So I'm going to look for the cats. And I'm going to look for the dogs. So all of these people here like cats. All of these people here like dogs. I want to know which ones like cats and dogs. It's the 6 and this 2 right here. That's the cat and the dog lover right there. So I have 8 out of the 40. Problem number 4 says probability they like cats or dogs. Okay, so the difference between this is still going to be 40. So cats or dogs. There's only one person here out of our 40 that doesn't have a cats or a dog love. That one right there. So we have 39 out of 40 that we would select somebody in this group that would like cats or dogs. You only have that one bird person that doesn't like cats or dogs. Okay? Problem number 5 says the student likes all 3 animals. How many is that? 2. 2 out of the 40. And then number 6, squeeze this in here. Number 6, probability the student does not like either birds or dogs. No birds, or dogs. Okay? Probability they don't like birds or dogs. So that's only going to be these 10 people here. These 10 people are the only ones that don't like birds or dogs. They only like cats only. You know, cats rule, dogs drool, right? And then number 7 gets into the conditional probability. So the probability they like cats such that they like dogs. Okay? So we're going to go to the dog population. The dog population is this purple circle. So I got 15, 16, 17, 18, 19. So I have 19 people who like dogs. And then of those people who like dogs, how many of them like cats in that purple circle? How many are overlapped with cats? 6 plus 2, 8. Okay, so basically how that takes place is we have our 40 people that are involved. We say, okay, those of you who like dogs, stay here. So everyone who has dogs stays here. Everyone else goes out. And then what's the probability to choose somebody who likes cats as well? It's the overlap and the triple overlap that would fall into that category. Number 8 says a person likes birds but does not like cats. No cats. Okay? So birds such as no cats. Okay, so any of these people here in this region here like cats. Okay, so I'm not going to count that 10, 10, 6, and 2. I'm going to count the 1, 2, and 9. So that's going to give me 12 people. And of those 12 people, how many of those 12 people like birds? 3. There's 3 that like birds such that the people don't like cats. Like, hey, if you don't like cats, stay here. If you like cats, go away. And then you pick how many would like birds is in that category. And then 9. So problem number 9 says all 3 such that they like cats. Okay? So cats is, oh wait, number 9 likes cats. So I'm going to count up the whole cat circle. So I have 10, 10, 6, 2. So that's 28. That's my denominator. And they like all of them. So all of the animals is that 2. Okay? The results, cats and birds are not mutually exclusive. Explain how that statement means in the context of this question. So a person couldn't like both cats and dogs, so they're not mutually exclusive. You don't have to like cats, but you can't like dogs or anything like that. And then the results, cats and birds, is not independent. Explain what the statement means in the context. The chance that someone likes birds is changed if we know they like cats. So something like that, it would mean it's not independent. Okay. The second page, don't stress too much about. Let's go to the birthday paradox. This is, I got to get to the notes. 4-7, right? 4-6, didn't make the book for some reason. Oh, okay. So I'm just going to be on page 211.
Oh, with the homework?
Yeah, and the homework. So we're going to just talk about this for a second. They're going to call this the birthday problem in Simpson's paradox. So I think, okay. Says there are 2 treatments for tumors. We'll call them A and B. Success rates for both small and large tumors are shown below. The results were combined for a total success rate. So we have that diagram on 211. So we have treatment A, treatment B, small tumors, large tumors, 85 people in treatment A, 79 people in treatment B, things like that. In your own words, write how Simpson's paradox. But hang on, 4-7. There is not notes for 4-7, is there? I might be dumb, but I don't see. I don't know what Simpson's paradox is, so I guess we're going to skip that. Okay. Let's go down. Let's talk about just kind of the birthday chances. Okay. So I've heard this problem a long time ago. If you have 30 people in the same room, the chance that two of them were born on the same day, not necessarily the same year, but like let's say March 15th, the probability that two people are born on March 15th when you have like 30 people in the room is relatively high. Okay, so if we look at problem number one, what is the probability two people born January 1st? Okay. All right, so we're going to do this without a leap year. So are we okay with 365 days? Okay. So I'm going to say that I have a 1 in 365 chance times a 1 in 365 chance. Okay, that two different people are born on the same day. But if we go here, I'm going to show you, because we don't have the notes on it, Google birthday same day. Birthday same day probability. All right. What is the birthday paradox? We're taking a shot in the dark, see if we can find this. All right, what is the birthday paradox? It isn't a paradox. Two, it's easy to solve. Okay. I was born on the 2nd of August, exactly 33 years before my father was born. I always taught the fact that sharing a birthday with my dad was something really unique. I don't have two friends who are born on the same day. I never really thought about the math of two people having the same birthday. If a friend of mine hadn't talked to me about the birthday paradox, I probably would. He said, "You're at a party. There are exactly 23 people in the room. What are the odds of two people sharing the same birthday?" I said, "I don't know, but it's pretty low." And then he says, "Actually, it's more than 50%. Shut up. No way that's true. As it turns out, to solve this problem, we have to answer the simple question. How many people do we need to have a probability of two of them sharing the same birthday be more than 50%? So, before we begin, we have to make some assumptions. First, consider a year is 365, no leap years. This means that I have a 100% probability that we will need 366 people. The second assumption is that of the 365 birthdays are equally likely. In reality, it is not true, but the results are more affected only slightly. Actually, this is the worst case. Okay, solution. Okay. So let's start simple. The chance that two people share the same birthday, the first person can be born on any day of the year. This means that the probability is 365 out of 365. The second person can be born on the same day, and there is a 1 in 365 chance of this happening. If these events happen at the same time, the probability comes out to about 0.27%. Okay? So if you only have two people, you have a 0.27% chance that they would share the same day that they were born. All right. So now we consider if we have three people, probability A and B have the same birthday, B and C, A and C, A, B, and C have the same birthday. It's not too difficult. However, we have to go a little bit larger. So let's take a look at the math. Okay, so we have 365 out of 364 times 365 out of 364 out of 365. So the probability of two people that don't have the same birthday is that. Okay, so 0.9 or 99.7% of chance. The 365, 3 out of 365 means the person can be born on any day of the year. However, you want the second person doesn't share the birthday with the first, we have to conclude from that number the possible birthdays for the second chance. So they're doing this because you're talking about 365 days where you're only talking about 364 actual days that you're going to work with. And then as you go through with 3 people, the chance that 3 people don't share the same birthday is 99.17%. Why did this do this? Okay, so if this continued to go on and on, basically you're taking 1 out of 365 to the 23rd power. So if you have 23 people, you're going to multiply all the days up. So 1 out of 365 raised to the 23rd power. If you had 23 people, you have a 49.27% chance, or so 49.3% chance that they don't share the same birthday. That means you have better than a 50% chance that they will, and that's only with 23 people. Okay? It's a little bit different to kind of think about this stuff, but it's a logistical curve. So probability, 23 people, probability is 50.7. If we have 30 people together, we have a 70.6% chance that 2 people would share the same day that they were born on. If you have 40 people, it's 89.1. 50 people, 97%. If you have 75 people, you have a 99.97% chance that at least 2 of them would be born on a similar day. So the probability increases, but it gets closer and closer to 100%. It's exactly 100% if you have 366 people in the situation. So now you might be wondering why this problem is a paradox. As you would be right, it is not. However, the fact is there is more than 50% chance that 2 people born on the same day in a small group of 23 is counterintuitive. The main reason in the group is 23 compared to the birthday of others. Only make a 22 comparison. That means there are only 22 chances of sharing the same birthday. However, we don't make only 22 comparisons. The number is much larger. So if you add the summation of 22 plus 21 plus 20 all the way down, that's 253. So in total, we make 253 comparisons. There's a lot more than 22, blah, blah, blah. All right. So because I don't have the lecture material on that, we're not going to stress too much about working for 7. So I would like us to, because we went through that paradox, just kind of a fun little thing to look at. Let's have us work on page 213, 214. And this will be due at the end of the period tomorrow. Let's see. I think. Okay. Holy cow. All right. We're actually going to do 214 to 217, but this is a work in progress. Call it a WIP. Work in progress, meaning I will go over as much of it as I can tomorrow, which is Thursday, to prepare us on our test on our quiz on Friday. Okay. That's it. Cool. I gotta take it. First, take it.